a galaxy blazes across 13.4 billion light-years of space. It should not exist. When we peer at this distant system, we see it as it was less than 300 million years after the Big Bang. At that time, the universe was only 2% of its current age. In that primordial epoch, only hydrogen and helium were supposed to exist. Yet this tiny galaxy burns with the unmistakable signature of oxygen. Oxygen is an element that demands generations of stars to form, live, and die in violent explosions. This impossible discovery is rewriting the first chapter of cosmic history. We are about to witness shocking chemistry that should not be there. We will reveal what this single point of light means for everything we thought we knew about the birth of galaxies. Scientists have found something that breaks every rule. A fully formed galaxy exists when the universe was less than 300 million years old. Picture the entire history of the cosmos compressed into a single calendar year. This galaxy showed up bright and mature on January 7th. Everything we understand about chemistry, star formation, and the flow of time says this should not be possible. The discovery came from a tiny, unremarkable point in the constellation Fornax. When astronomers aimed the James Webb Space Telescope at this region, they expected to see the faint, primitive structures of the early cosmos. Instead, they found a system blazing with a level of chemical complexity that should have taken billions of years to develop. The galaxy's official designation reads as a string of letters and numbers. The scientists who found it simply call it the record holder. It sits 13.4 billion light-years away. Here lies the core of the problem. At 300 million years after the Big Bang, the universe was a mere infant. To compare it to a human baby, displaying the knowledge of a teenager, would actually understate the situation. This galaxy contains significant amounts of oxygen. This element demands multiple successive generations of stars to create it. Each of those generations requires millions of years to form, burn its fuel, and then die in a spectacular explosion. The math simply refuses to work. Traditional models of cosmology predict that galaxies at this epoch should be small, dim, and chemically simple. This one violates all three of those predictions. It shines with a brightness that exceeds expectations by factors that make astrophysicists profoundly uncomfortable. Its size extends across 1,600 light-years, making it substantial rather than a compact, nascent knot. Most shocking of all, Webb's instruments detected a strong and undeniable signature of oxygen mixed throughout its structure. The element oxygen forms only inside the cores of massive stars through the process of nuclear fusion. Those stars must then explode as supernovae to scatter their elemental contents across the vastness of space. New stars then form from this enriched material, continuing the cosmic cycle of creation. This process cannot happen quickly. The laws of physics impose strict speed limits on stellar evolution that cannot be circumvented. The research teams calculated backward from the observed levels of oxygen. They determined that the galaxy must have been forming stars for a period of potentially 100 million years before the moment we are observing it. That pushes the dawn of star formation back to within 200 million years of the Big Bang. At that time, the universe had barely had time to cool from its initial fiery expansion. Dense clouds of gas had barely had time to begin collapsing under the slow, patient pull of gravity. Yet somehow this system managed to assemble itself, ignite multiple generations of stars, and create complex chemistry at a pace that our current theories cannot explain. Two independent teams of scientists verified these astonishing findings using different instruments. The near-infrared camera captured the initial faint images. The mid-infrared instrument was what revealed the shocking signature of oxygen. Later, radio observations from the Atacama Large Millimeter Array in Chile confirmed the oxygen detection with extraordinary precision. The measurements align perfectly across different wavelengths and from different observatories. What you see here challenges the very foundations of cosmology. Time itself becomes the villain in this cosmic story. The universe has rules about how fast things can happen. Stars need time to form, they need time to burn their fuel, they need time to die and spread their ashes. Every single step in this process requires millions of years. This galaxy appears to have completed the entire sequence before it even had the time budget to do so. Think about baking a loaf of bread. Mixing the ingredients takes only a few minutes, but the dough needs hours to rise. Baking requires still more time in the oven. You cannot simply compress these steps. The chemistry demands its own required duration. Stellar alchemy, the creation of elements inside stars, works in much the same way. Hydrogen fuses into helium over millions of years in the cores of stars. Heavier elements are then formed through a sequence of burning stages as the star ages. The final cataclysmic explosion only happens after the star has exhausted all of its possible fuel sources. The numbers for this galaxy create an impossible equation. It appeared 290 million years after the Big Bang. The oxygen in its spectrum is present in quantities that match galaxies that are billions of years older. The very first stars needed time to collapse from the primordial gas clouds. Our best estimates place the first star formation no earlier than 100 to 200 million years after the bang. This leaves a window of perhaps 150 million years at the absolute maximum. Within that impossibly short window of time, a whole sequence of events must have occurred. The first generation of stars, the so-called population 3 stars, must have formed from pure hydrogen and helium. These stars were likely massive giants, perhaps 30 to 300 times more massive than the stars we see today. Such giants would have burned incredibly hot and bright, exhausting their fuel in a mere few million years. When they exploded, they would have dispersed oxygen, carbon, and other heavy elements into the surrounding gas. That newly enriched gas would then have had to cool and collapse all over again. A second generation of stars would have then formed from this material. Some of these stars would also have had to burn through their fuel and explode. The cycle would have had to repeat. Each iteration adds more and more heavy elements to the mix. The concentration of these elements builds up gradually over time. To reach the levels of oxygen detected in this galaxy, multiple cycles would be required. Each of those cycles takes a time that is measured in millions of years. Computer simulations of early universe star formation consistently show that building up a significant amount of metal content takes much longer than this galaxy had available. The models include factors like gas, cooling rates, gravitational collapse, timescales, and the various phases of stellar evolution. Even when pushing every single one of these assumptions to its absolute physical limit, scientists cannot make the timeline work under the rules of conventional physics. Some researchers have proposed that the early stars formed much faster than our current models predict. Others have suggested that the supernovae dispersed their contents more efficiently in the denser environment of the early universe. A few radical theories have proposed that the first stars were far, far more massive than we believed, allowing them to burn and die on accelerated timescales. None of these explanations feels fully satisfying. Each one requires a significant reworking of our fundamental assumptions about how gravity, pressure, and nuclear fusion operate. The timeline problem extends beyond this single galaxy. The James Webb Telescope has found other systems at similar distances that show an unexpected level of maturity. The pattern suggests that this is something systematic rather than just a statistical fluke. The universe, it seems, managed to master the art of galaxy formation far faster than our best theories ever predicted. How it did so remains a terrifyingly unclear mystery. Imagine crushing everything in existence into a space smaller than the period at the end of this sentence. All matter, all energy, all of space itself. This is what scientists call the singularity, the point where our universe supposedly began. But there is a massive problem with this idea that physicists rarely discuss openly. The mathematics of our theories completely falls apart at this moment. When you try to calculate what happened at the very instant of the Big Bang, the equations return the answer of infinity. The temperature becomes infinite, the density becomes infinite, the curvature of space becomes infinite. To a mathematician, infinity is not just a really big number. It is a red flag screaming that something fundamental has gone wrong with your theory. General relativity, Einstein's masterpiece that describes gravity and the shape of space, works brilliantly almost everywhere else in the universe. It successfully predicts the existence of black holes. It explains why the clocks on GPS satellites need to have time corrections. It tells us how massive galaxies are able to bend the path of light. But at the singularity, general relativity breaks down completely. The theory that explains almost everything suddenly explains nothing at all. This creates what physicists call the singularity problem. If our best theory of gravity cannot describe the most important moment in the history of the cosmos, then we are missing something crucial. Stephen Hawking spent decades of his life wrestling with this very puzzle. Roger Penrose won a Nobel Prize in part for proving that singularities are an inevitable consequence of Einstein's theory. Both of these men eventually concluded something truly radical. Maybe the singularity never actually existed. Think about what this means for a moment. Every single atom in your body, every star in the sky supposedly exploded from a point of mathematical impossibility. The entire universe is said to have emerged from a point where the laws of physics themselves cannot operate. This is not science. This is not even close to being an explanation. The problem gets even worse when you try to add quantum mechanics into the mix. Quantum physics is the theory that describes the behavior of tiny particles. It has its own set of rules that often contradict the rules of general relativity. At the incredibly small scales of the supposed singularity, quantum effects should have been dominant, but we do not currently have a working theory that is able to combine quantum mechanics with gravity. We are literally blind to what happened at that most critical of instants. Some physicists argue that we should just accept the singularity as the beginning of time itself. Before that moment, there was no before. Time itself started ticking at the moment of the bang. But this explanation feels a bit like giving up. It is like a detective finding a crime scene with no footprints leading to it and simply declaring that the criminal must have appeared from nowhere. Others suggest that we need a complete theory of quantum gravity to be able to see what really happened. And over the past 20 years, several such theories have begun to emerge. These new frameworks are revealing something extraordinary. The singularity might be nothing more than an illusion. Instead of a beginning from absolute nothingness, these theories predict that something existed before. Our universe might not be the first act in the grand history of the cosmos. It might just be the sequel. What if the Big Bang was not actually a beginning but a transition? Roger Penrose is not a man who makes wild claims lightly. At 94 years old, he has spent 7 decades of his life doing mathematics that most people cannot even begin to read. He has proven fundamental theorems about the nature of space and time. He has invented new ways to visualize the universe. In 2020, he won the Nobel Prize in Physics for his groundbreaking work on black holes. Then he proposed something that made his colleagues deeply uncomfortable. Penrose claims that he has found evidence that our universe existed before the Big Bang. Not just theoretical evidence, but actual observations in the sky that point to a previous cosmic era. He calls his idea conformal cyclic cosmology. The name may sound technical, but the concept is stunning in its implications. According to Penrose, the universe is not a one-time event. It goes through an infinite number of cycles. Each cycle begins with what we call a Big Bang and ends in a strange, far future state. Then something remarkable happens. The ending of one cycle becomes the beginning of the next. Our universe is just one single chapter in an eternal and unending book. This is not some fringe science from an unknown researcher. This is a Nobel laureate saying that everything you have learned about the origins of the cosmos might be completely wrong. Penrose published his full theory in a book that was titled Cycles of Time in 2010. The scientific community reacted with a mixture of both fascination and skepticism. Some called it brilliant, while others called it impossible. What makes Penrose's idea different from other speculative theories is that it makes predictions that we can actually test. He claims that violent events from the previous universe should have left their marks on our own universe. Specifically, he looked for unusual patterns in the cosmic microwave background, which is the faint glow of radiation that fills all of space. This glow is like a baby photo of our universe, showing us what the conditions were like just 380,000 years after the Big Bang. Penrose and his collaborators analyzed the data from the satellites that have mapped this radiation. They claim to have found exactly what their theory predicted: circles of abnormal temperature, which they have called Hawking points. These points, according to Penrose, are the final evaporations of supermassive black holes from the universe that existed before ours. The radiation from those ancient dying black holes supposedly survived the transition between universes and now appears as hotspots in our own sky. Many scientists immediately tried to disprove these claims. Multiple different research teams analyzed the same data, but they used different methods. They found that the circles that Penrose had identified were no more unusual than the random fluctuations that you would expect to see from pure chance. The debate became quite heated. Papers and counterpapers flew back and forth in the scientific journals. Penrose, however, remained undeterred. In 2018, he published a new analysis that claimed even stronger evidence. He had identified hotspots that were significantly hotter than their surrounding regions, far beyond what random chance should be able to produce. The temperature differences were about 10 times larger than the cosmic average. Again, his critics argued that similar patterns appeared in their simulated universes where no previous cosmos had existed. The controversy continues to this day. Penrose's reputation means that his ideas cannot simply be ignored, but the evidence for them remains highly disputed. What is clear is this: a brilliant mind has looked at the same universe as everyone else and has seen something that others have missed. Whether he is right or wrong, his theory has opened a door that many people thought was permanently sealed. It is the door to what existed before. To understand how one universe could possibly become another, you need to grasp a strange property of space and time. Penrose built his entire theory on something called conformal geometry. This is a branch of mathematics that studies shapes and distances, but with a unique twist. It focuses on angles and the paths that light takes, while completely ignoring the concept of absolute sizes. Here is why that is so important for cosmology. Imagine the universe in the incredibly distant future, trillions upon trillions of years from now. All of the stars have burned out. All of the matter has either decayed or fallen into black holes. Those black holes themselves have slowly evaporated through a quantum process known as Hawking radiation. What remains is a nearly empty space filled only with photons, which are particles of light racing away from each other as the universe continues to expand. In this remote future, nothing in the universe has mass anymore. Everything that could possibly decay has already decayed. The universe is cold, dark, and consists almost entirely of radiation that is spreading out through an ever-expanding space. This is where Penrose saw something profound. Particles that have mass are the ones that experience time. They age. They have internal clocks. But massless particles like photons do not experience time in the same way. For a photon, the journey from one end of the universe to the other happens instantaneously from its own perspective. When the universe finally reaches this state of pure radiation with no massive particles left, something truly bizarre becomes possible. The very concept of size becomes meaningless. If you have no rulers that are made of atoms, no clocks that are made of matter, and no reference points that have any mass, then you have no way to measure distances or durations. The universe effectively loses track of its own scale. Penrose realized that you could take this far future universe and mathematically transform it. Using the principles of conformal geometry, you can actually rescale it so that the infinite expanse of the dying universe becomes the infinitely small point of a new Big Bang. The ending and the beginning are actually the same event, just viewed from two different perspectives. It is like looking at the two sides of the same coin. This transformation is not just an arbitrary mathematical trick. It preserves the geometry that is important for light and radiation. The paths that the photons take in the old universe become the paths that the photons take in the new one. Any information that is encoded in the light could theoretically survive this transition. The new universe does not start from a state of nothingness. It inherits a certain amount of structure from its predecessor. This rescaling also solves several deep and persistent problems in cosmology. In the standard Big Bang theory, we have to ask the question of why the universe started in such a special low entropy state. Entropy is a measure of disorder, and our universe began in an incredibly ordered state. Where did all of that order come from? Penrose's cycles provide a potential answer. The order comes from the smooth, empty state that exists at the end of the previous cycle. The far future naturally produces the low entropy conditions that are needed for a new beginning. There is another significant advantage to this idea. The uniformity of our universe has always been a puzzle for cosmologists. Why does the cosmic microwave background look nearly identical in every single direction we look? Why did regions of space that could never have possibly communicated with each other all end up at the same temperature? Standard cosmology invokes a process called inflation, a brief period of faster-than-light expansion, to try to explain this. But inflation has its own set of fine-tuning problems. In conformal cyclic cosmology, this uniformity emerges naturally from the previous cycle. The long period of expansion in the old universe is what smooths everything out. When that smooth ending becomes the new beginning, the uniformity simply carries over. No inflation is needed. No special initial conditions are required. The universe simply inherits its properties through a form of cosmic inheritance. Critics, of course, point out some significant challenges to this idea. How exactly does this transition work? What happens to any matter that has not yet decayed? Can information really survive such a dramatic transformation of scale? Penrose admits that some of the details of his theory remain unclear, particularly the physics at the crossover surface, where one cycle ends and the next one begins. He argues that this is precisely where a theory of quantum gravity must take over, filling in the gaps that classical relativity cannot address. Whether conformal cyclic cosmology is ultimately correct remains unknown. What cannot be denied is its sheer elegance. The idea that endings and beginnings are connected, that the universe is eternal and self-renewing, carries a certain profound beauty. But beauty alone is not what makes a theory true. The cosmic microwave background is the oldest light in the entire universe. When astronomers point their instruments at the empty space between the galaxies, they can detect this faint uniform glow. It comes from every direction in the sky with a temperature of about 2.7 degrees above absolute zero. This radiation was released just 380,000 years after the Big Bang, when the universe had cooled enough for atoms to form and for light to begin to travel freely. Scientists have now mapped this ancient glow in extraordinary detail. Satellites like WMAP and Planck have measured tiny variations in its temperature across the entire sky. Some regions are slightly warmer, about 1 part in 100,000, hotter than the average. Other regions are slightly cooler. These tiny variations represent the seeds that would eventually grow into the galaxies and clusters of galaxies that we see today. But Penrose was not looking for these well-known fluctuations. He was hunting for something entirely different. He was looking for circular patterns that would indicate the presence of Hawking points. According to his theory, the supermassive black holes from the previous universe would have gradually evaporated through the process of Hawking radiation. This is a quantum effect where black holes slowly lose their mass by emitting particles. For a black hole with the mass of billions of suns, this process takes an incomprehensible amount of time. We are talking about 10 to the power of 100 years, a duration with 100 zeros after it. Eventually, though, each black hole would completely evaporate in a final brilliant burst of energy. These bursts would have been the last energetic events to occur in the dying universe. When the conformal rescaling happened, turning the far future into a new Big Bang, these bursts would have left their imprints. They would appear as specific types of anomalies in the cosmic microwave background of the new universe, which is our universe. Penrose predicted that these imprints would look like circular regions where the temperature falls off in a characteristic way from a central hotspot. These circles would have diameters of about 5 times the width of the full moon in our sky. They would not be obvious to a casual inspection, but a statistical analysis of the data should be able to reveal them. In 2010, Penrose and the physicist Vahe Gurdzadyan claimed that they had found exactly these patterns. They had scanned the data from the WMAP satellite and had identified numerous concentric circles where the variance in the temperature was significantly lower than expected. They calculated that the probability of seeing so many of these circles by random chance was extremely small, less than 1 in a billion. The announcement created an immediate controversy in the scientific community. If their findings could be confirmed, it would completely revolutionize our understanding of cosmic history. Multiple research teams rushed to check their findings. Within just a few months, 3 independent groups had published rebuttals. They had analyzed the same data and had found no unusual excess of circles. When they created simulated universes using standard cosmology with no previous cycles, those simulations produced just as many circular patterns as the real data. The disagreement ultimately came down to the methodology. How do you decide what counts as a significant circle? How do you properly generate random simulations to compare against? These technical questions became the new battlegrounds. Each side accused the other of having flawed statistics. Undeterred, Penrose refined his approach. In 2018, he published a new analysis with Daniel An and Krzysztof Meissner. This time, instead of looking for circles with a low variance, they searched for concentrated hotspots. They found patches in the cosmic microwave background that were significantly hotter than their surrounding regions. Around these hotspots, the temperature gradient was much steeper than in any of their simulated universes. Not a single one of their simulations out of 1,000 was able to match the real data. They argued that these hotspots were exactly what you would expect to see from Hawking points. The final evaporation of a black hole would inject an enormous amount of energy into a very small region. That energy would then be stretched during the early expansion of the new universe, creating a hot patch with a characteristic size and temperature profile. Again, the broader community of physicists remained skeptical. Many of them felt that the analysis was comparing apples and oranges. The simulations might not be capturing all of the complexity of the real universe. Other groups noted that if you search for enough different kinds of patterns in noisy data, you will eventually find something that looks special just by chance alone. As of now, the existence of Hawking points remains unproven. The cosmic microwave background is one of the most precisely measured things in all of science. Yet, interpreting its fine details is a surprisingly subjective process. But one thing is certain. If those hot spots in the sky really are the echoes from a previous universe, then we are not just looking at old light, we are looking at ghosts. The universe that we see today is a messy place. Galaxies are clustered together in long filaments and vast sheets. Stars are constantly burning and exploding. Black holes are devouring matter. Disorder is everywhere. This messiness is what is known as entropy. It is the measure of how spread out and disorganized energy becomes over time. The second law of thermodynamics states that entropy always increases. Everything in the universe tends toward a state of disorder. Your room will get messy, unless you actively work to clean it. Stars will eventually burn out. Even atoms themselves will decay if given enough time. Yet the Big Bang apparently started in an incredibly ordered state. This is one of the deepest and most persistent puzzles in all of cosmology. When we look at the cosmic microwave background, we see an almost perfectly smooth and uniform universe. The temperature variations are only 1 part in 100,000. There are no significant clumps, no major irregularities, just gentle ripples in an otherwise uniform sea of energy. This extraordinary smoothness represents a state of extremely low entropy. So where did all of that order come from? In the field of statistical mechanics, which is the branch of physics that studies entropy, low entropy, states are spectacularly improbable. Imagine throwing a full deck of cards up into the air. The probability that those cards will land on the ground in perfect numerical order is essentially 0. Now imagine that the deck of cards contains not 52 cards but 10 to the power of 90 particles. That is roughly how many particles exist in the observable universe. The odds of them starting out in such a highly organized configuration are incomprehensibly small. Standard Big Bang cosmology does not offer an explanation for this initial state of order. It simply assumes that the universe started out that way. Physicists call this assumption the past hypothesis. We hypothesize that the entropy was very low at the beginning of the universe because, well, our observations show us that it was very low. This is not an explanation. This is just a restatement of the puzzle but with fancier words. Roger Penrose calculated just how special this initial state of the universe actually was. He estimated that the gravitational degrees of freedom at the moment of the Big Bang were tuned to a precision of 1 part in 10 to the power of 10 to the power of 123. Let that number sink in for a moment. It is a 1 followed by 10 to the power of 123 zeros. Writing out that number would require more digits than there are atoms in the entire universe. This is what Penrose calls the Weyl curvature hypothesis. The Weyl curvature is a measure of the type of gravitational field that is associated with tidal forces and gravitational waves. In an irregular, lumpy universe with black holes and collapsed structures, the Weyl curvature is enormous. But at the moment of the Big Bang, it was essentially 0. Gravity at the very beginning of the universe was incredibly smooth and uniform. This smoothness is the source of the universe's low initial entropy. So why would the universe start out in such an absurdly improbable state? Cosmic inflation provides one possible answer. If the universe underwent a brief period of exponential expansion right after the Big Bang, that expansion would have smoothed out any initial irregularities. It is like stretching a wrinkled bed sheet. If you pull the edges fast enough, the wrinkles will disappear. But inflation has its own fine-tuning problems. You need very specific starting conditions for the process of inflation to even begin. You need a special type of energy field called the inflaton that behaves in just the right way. Many physicists feel that this has simply moved the entropy problem one step backward. Instead of asking why the Big Bang was so smooth, we are now asking why the inflaton field was so smooth. Cyclic models offer a different kind of resolution to this problem. If our universe emerged from a previous universe, then that previous universe is what provided the initial conditions. The far future of the old universe naturally becomes smooth as space expands and matter spreads out. When that smooth ending transitions into a new beginning, the state of low entropy simply carries over. The past hypothesis is no longer an assumption. It is a direct consequence of cosmic recycling. But this creates yet another question. What about all of the entropy from the old universe? If entropy is always increasing and the new universe is inheriting its conditions from the old one, then shouldn't each cycle become more disordered than the last? This is known as the entropy problem in cyclic cosmology. Some models propose that the universe grows slightly larger with each successive cycle, which would provide more room for the entropy. Others suggest that black holes serve as a kind of entropy sink, and that they are somehow reset during the transition. These solutions remain controversial and incomplete. The mathematics of what happens during the bounce or the transition is still not fully understood. We are asking questions about physics at energy scales that we cannot possibly test in our laboratories at the moment. We only have our theories and our best guesses to go on. What we do know for certain is that the universe's remarkable initial smoothness demands an explanation. Either something extraordinary happened before the Big Bang to set up those conditions, or the Big Bang itself was far more special than our current theories suggest. Neither of these options is easy to accept. Deep beneath the smooth and uniform appearance of space lies something truly profound. Most people think of space as being just emptiness, a kind of stage where matter and energy perform their cosmic dance. But quantum physics suggests that reality is far more complex than that. Even the vacuum of space has a structure, and that structure might be what saves the universe from the singularity problem. Loop quantum gravity is one of the leading approaches to merging the theory of quantum mechanics with Einstein's general relativity. It starts with a radical and counterintuitive idea. Space itself is not infinitely divisible. You cannot just keep zooming in to smaller and smaller distances forever. Eventually you will hit a fundamental limit, which is known as the Planck length, which is about 10 to the power of minus 35 meters. This is 20 orders of magnitude smaller than a single proton. At this incredibly small scale, space is not a continuous fabric. It is granular, made of discrete quantum units. Think of it like the pixels on a computer screen. From far away, an image looks smooth and continuous, but if you get up close, you can see that it is composed of individual colored dots. Space, according to loop quantum gravity, is similarly pixelated at the Planck scale. These pixels are not static. They are dynamic loops of the gravitational field quantum fluctuations that weave themselves together to form the very fabric of space-time. The theory gets its name from these fundamental loops. Instead of describing gravity as the curvature of a smooth space, loop quantum gravity describes it as a network of interconnected loops. These networks are called spin networks, and they represent the quantum state of geometry itself. This picture changes absolutely everything about singularities. In classical general relativity, when matter collapses under the force of gravity, it can be compressed to an infinite density at a single point. Infinite density means an infinite curvature of space. The equations blow up and physics stops working. But in loop quantum gravity, an infinite compression is simply impossible. You cannot squeeze anything down to a size that is smaller than the Planck scale, because there is no space that is smaller than a Planck length. As matter collapses and its density grows, the quantum effects become stronger. When the density finally reaches the Planck density, which is about 10 to the power of 93 grams per cubic centimeter, something dramatic happens. Gravity itself becomes repulsive. The collapsing matter then bounces back outward. Instead of a singularity, you get a bounce. This prediction led to the development of loop quantum cosmology, which is a simplified version of the full theory that is applied to the entire universe. In the early 2000s, the physicist Martin Bogerwald showed that when you use loop quantum cosmology to model the Big Bang, the singularity completely disappears. The universe does not begin from an infinitely compressed point. It actually rebounds from a previous contracting phase. Imagine running the history of the cosmos backward. The galaxies get closer and closer together, and the universe gets smaller and denser. In standard cosmology, you would eventually hit the singularity and your equations would break down. But in loop quantum cosmology, as you approach the Planck density, a quantum repulsion takes over. The contraction reverses into an expansion. There is no moment of infinite density. The Big Bang becomes a big bounce. Detailed simulations have confirmed this behavior. Researchers have evolved the quantum states of the universe, both forward and backward, through the bounce point. The quantum effects smoothly connect the contracting and expanding phases of the universe. Crucially, some of the information from the contracting phase is able to survive the bounce. The volume of the universe, at its minimum point, and the rate of its expansion after the bounce are both dependent on the conditions that existed before the bounce. This means that we could potentially learn about the pre-bounce universe by studying our current universe. Observations of the cosmic microwave background, or the distribution of galaxies, might contain the signatures of quantum gravity effects that occurred during the bounce. These would be extraordinarily subtle signals, but they would be real. Loop quantum cosmology also solves another long-standing puzzle, which is known as the horizon problem. In standard cosmology, distant regions of the universe that have never been in communication with each other somehow have nearly identical properties. How did they manage to coordinate their temperatures? Inflation provides one possible answer: by making the observable universe originate from a tiny, causally connected region that then expanded with incredible speed. Loop quantum cosmology offers an alternative solution. During the contracting phase that occurred before the bounce, the regions that are now far apart were once in contact with each other. They came to a state of equilibrium back then. When the universe bounced and then began to expand, that state of equilibrium was preserved. No inflation is needed. The theory is not without its challenges, however. Loop quantum gravity itself is still an incomplete theory. We do not yet have a full mathematical formulation of it that works in all situations. The cosmological models that are used are simplified, assuming a perfect symmetry that the real universe does not actually have. Extending the theory to less symmetric situations is an incredibly difficult task. Moreover, some physicists question whether loop quantum gravity is the right approach to quantum gravity at all. Competing theories like string theory take a completely different path to the problem. Each of these different approaches makes different predictions about what happens at the Planck scale. What is clear is that the quantum effects at the very smallest scales can have cosmological consequences at the very largest scales. Space itself might be the key to understanding where we all came from. For decades, the Big Bang was the founding myth of modern cosmology. Everything was said to have started from a singular point 13.8 billion years ago. Before that moment, nothing existed. Not space, not time, not even the laws of physics. The Bang was the absolute beginning, and asking what came before it was considered to be a meaningless or even an unscientific question. That certainty is now beginning to crumble. Multiple independent lines of research now point toward a bounce rather than a bang. Not a creation from nothing, but a transition from something that existed prior. The universe did not simply begin, it changed its form. This shift in perspective is as profound as the Copernican revolution which displaced the Earth from the center of the cosmos. The Big Bounce hypothesis comes in several different versions, but they all share a few core elements. Our universe was preceded by a contracting phase. As that previous universe collapsed, instead of forming a singularity, the effects of quantum gravity intervened. Repulsive quantum forces halted the collapse and then reversed it into an expansion. This reversal is what is known as the bounce. Loop quantum cosmology provides the most developed framework for understanding how this bounce could have occurred. As we discussed earlier, the discrete structure of space at the Planck scale is what prevents an infinite compression. When the density of matter reaches a critical value, which is roughly 10 to the power of 93 grams per cubic centimeter, the quantum corrections to Einstein's equations become dominant. These corrections include a repulsive term that grows very rapidly at these extreme densities. The mathematics of the theory shows that the bounce is not an instantaneous event. There is a brief quantum epoch which lasts for about 10 to the power of minus 43 seconds, where our classical notions of space and time break down. During this period, the universe passes through its minimum volume. Then the quantum repulsion takes over completely and begins to drive the expansion that we observe today. So, what happened in the contracting universe that existed before the bounce? Here, the evidence becomes much more speculative. Some models suggest that the previous universe was very similar to our own, with galaxies and stars, but just running in reverse time. Others propose that the contracting phase had very different properties. The matter content, the spatial geometry, and even the effective constants of nature might have been different. One intriguing possibility is that information could have survived the bounce. Unlike the singularities of black holes, where information appears to be destroyed, the bounce is smooth enough that quantum states might be able to pass through it. The scalar fields that represent matter and energy evolve in a continuous manner. Their values after the bounce are dependent on their values before the bounce. This creates what physicists have called a quantum bridge, which connects the two phases of the universe. If information is able to survive, then relics from the pre-bounce universe could still exist in our own. These would not be physical objects. Atoms and molecules could not possibly survive the extreme conditions that would exist near the bounce point. But subtle correlations in the quantum fields might be able to persist. These correlations could then show up as specific patterns in our cosmological observations. Several different research groups have calculated what the cosmic microwave background should look like if our universe did in fact bounce. The predictions depend very sensitively on the details of the dynamics of the bounce, but some generic features do emerge. The spectrum of the temperature fluctuations might have some slight deviations from the standard predictions. The amount of gravitational waves that would be produced during the bounce could be different from what is predicted by inflation. The distribution of matter on the largest scales might also carry some subtle signatures of the bounce. So far, our observations have not definitively detected any of these bounce signatures. The cosmic microwave background matches the standard inflationary predictions remarkably well, but the precision of our current measurements is still limited. Future experiments with a higher sensitivity might be able to reveal the small anomalies that would point to a bounce. Critics of the bounce cosmology have raised several objections. The biggest concern is whether the bounce truly avoids a singularity or if it merely delays it. Some analyses have suggested that even with the quantum corrections, certain types of anisotropic collapses can still lead to singularities. If the universe was not perfectly symmetric before the bounce, would it still be able to bounce cleanly? Another worry is the issue of fine-tuning. For a bounce to be able to produce a universe like our own, the conditions at the bounce point must have been very carefully arranged. The quantum state would need to have had specific properties. The amount of matter and its distribution would have had to fall within some very narrow ranges. If the pre-bounce universe was chaotic and irregular, could the bounce really have smoothed everything out? These technical debates are continuing in the academic journals. What is remarkable is that mainstream physics is now seriously considering the possibility of a pre-existing universe. The Big Bounce is no longer just fringe speculation. It is a legitimate scientific hypothesis with mathematical rigor and potential observational tests. The implications of this idea are staggering. If the bounce is real, then the universe has a history that extends infinitely into the past. Or perhaps there was an earliest bounce, a first transition, and the mystery of the origin simply moves back to that moment. Either way, the Big Bang would lose its status as the ultimate origin of everything. We would not be witnessing the beginning of existence. We would be watching just one phase in an ongoing and eternal process. The idea of two universes that are connected by a quantum bridge might sound like something out of science fiction, but in the theory of loop quantum cosmology, it emerges naturally from the mathematics. This bridge is not a physical structure that you could ever see or touch. It is a continuous mathematical evolution that links the contracting phase of the universe to the expanding phase without ever reaching a point of zero volume. To understand this quantum bridge, you need to grasp how quantum mechanics treats the process of evolution. In classical physics, objects have definite positions and velocities at each and every moment. You can predict precisely where a ball will be if you know where it started and how fast it was moving. But in quantum mechanics, particles do not have definite positions until they are measured. They exist in a state of superposition, spread out across multiple possible locations at the same time. The universe in loop quantum cosmology is described by a quantum state, which is a mathematical object that is known as a wave function. This wave function encodes the probabilities of finding the universe with different volumes and different matter contents. As time progresses, this wave function evolves according to the quantum equations. This evolution is what is known as unitary, which means that information is preserved and that nothing is ever truly lost. When the universe contracts, its wave function evolves towards smaller and smaller volumes. In classical general relativity, this evolution would hit a singularity at a point of zero volume, and it would then stop. The equations would produce infinities and meaningless results. But in loop quantum cosmology, the evolution does not stop. The wave function is able to smoothly pass through the region of minimum volume and then emerge on the other side, corresponding to an expanding universe. This passage through the minimum volume is what is known as the quantum bridge. It is called a bridge because it connects two distinct cosmological phases. Before the bridge, the universe was contracting. After the bridge, the universe is expanding. The bridge itself only lasts for the briefest of instants, roughly 1 Planck time, which is about 10 to the power of minus 43 seconds. During this instant, our classical concepts of things like volume and time become fuzzy. You cannot ask the question, what was the exact volume at this precise moment? The question assumes a level of definiteness that quantum mechanics simply does not allow at such extreme scales. What you can ask is, what is the probability distribution for the volumes, and how does that distribution evolve? The calculations show that the distribution remains well behaved throughout the entire bounce. It does not spike up to infinity. It does not develop any discontinuities. The universe does not just blink out of existence and then reappear. It continuously exists as a quantum system, even if our classical intuitions about space and time begin to fail. One of the key features of this quantum bridge is that it is able to preserve certain quantities which are known as observables. In quantum mechanics, observables are the properties that you can in principle measure. For cosmology, the important observables include the total energy content, the spatial curvature, and the values of the various matter fields. The quantum bridge allows these observables to pass through the bounce point, with their specific relationships being maintained. For example, consider a scalar field that represents a type of matter. This field has a value at each point in space, and it evolves over time. If you know the behavior of this field during the contraction phase, you can use loop quantum cosmology to calculate its behavior after the bounce. The two are intrinsically linked. The scalar field after the bounce does not just start with random values. It inherits its structure from the scalar field that existed before the bounce. This inheritance is crucial for being able to make predictions. If we can measure the properties of our own universe with a precise enough accuracy, we might be able to reconstruct the properties of the pre-bounce universe. This would be a form of indirect detection, like inferring the shape of an object from its shadow. The measurements would be extraordinarily difficult to make, requiring a level of precision that is beyond our current technology. But they are in principle possible. Different scalar fields might be able to carry different types of information. Inflaton fields, if they exist, could encode data about the energy densities that were present before the bounce. Curvaton fields might be able to preserve information about the spatial geometry. Even the pattern of quantum fluctuations that was seeded during the bounce could reflect the conditions that existed before the bounce. However, not all of the information is able to survive. There is an effective uncertainty principle that operates at the point of the bounce. Just as you cannot simultaneously know a particle's position and its momentum with perfect precision, you cannot simultaneously know all of the properties of both the pre-bounce and the post-bounce universes with perfect precision. Some of the details are inevitably lost or scrambled by the quantum nature of the bounce. Physicists describe this process using a transfer function, which is a mathematical rule that maps the pre-bounce states to the post-bounce states. This transfer function is not a one-to-one mapping. Multiple different pre-bounce states could all lead to the same post-bounce state. This means that we cannot uniquely determine the entire history of the contracting universe just by studying the expanding one. Some level of ambiguity is fundamental. Despite this limitation, the concept of the quantum bridge represents a profound shift in our cosmological thinking. It suggests that the universe is not just fragmented into a series of disconnected epochs. The past, the present, and the future are all linked together by a continuous quantum evolution. The bounce is not a wall that is blocking our knowledge. It is a gateway, admittedly a narrow and obscure one, but a gateway nonetheless. What lies on the other side of this quantum bridge remains largely mysterious, but we now have the theoretical tools to begin to probe that mystery. The veil that separates the universes is beginning to thin. In 1979, the physicist Alan Guth was trying to solve some problems with the standard Big Bang theory. He was not thinking about multiple universes or an infinite cosmos. He just wanted to explain why the universe is so smooth and flat. The answer that he found changed everything. Guth proposed that the very early universe underwent a brief period of exponential expansion, which he called inflation. During this phase, which lasted for less than a trillionth of a trillionth of a trillionth of a second, the universe doubled in size at least 90 times. Space was expanding faster than the speed of light. This rapid growth would have smoothed out any irregularities and flattened the geometry of the universe, which solved several major cosmological puzzles. Inflation quickly became the leading theory of the early universe. But as physicists began to explore the mathematics of the theory more deeply, they discovered something that was completely unexpected. Inflation does not just happen once and then stop everywhere at the same time. In most versions of the theory, the process of inflation is eternal. Once it starts, it never completely ends. Here is how the theory of eternal inflation works. Imagine the universe filled with an energy field, which is called the inflaton. This field is what drives the process of inflation when its energy density is high. As inflation proceeds, this field gradually decays into lower energy states. In the regions where it decays, the process of inflation stops and a hot Big Bang begins. That region then becomes a pocket universe like our own. But here is the catch. Space itself is expanding exponentially. Even though inflation is ending in some places, the expanding regions that are between those places are growing much faster than the non-inflating regions can fill them. New volume is being created much faster than the old volume can be converted. The total amount of inflating space is therefore increasing without any limit. More and more pocket universes are forming forever. Think of it like the foam on the surface of the ocean. Each individual bubble represents a pocket universe where the process of inflation has ended. The foam that is between the bubbles is still in a state of inflation, and it is creating new bubbles endlessly. You can pop the individual bubbles, but the foam itself will never stop growing. The process is self-sustaining, and it is eternal into the future. Quantum fluctuations are what make this process inevitable. The inflaton field is subject to a kind of quantum jitter. In some tiny patches of space, random fluctuations can actually push the field up the energy hill instead of down it. Those patches will then inflate for a longer period of time, and they will produce more volume. Even if inflation is an unlikely process to start, once it starts anywhere, it will run away exponentially. The inflating regions will come to dominate the total volume of the universe. André Linde, who was one of the pioneers of inflation theory, proved in 1986 that eternal inflation is a generic feature of the theory. You do not need to have any special conditions for it to occur. Almost any model of inflation will lead to eternal inflation unless you very carefully design the theory to avoid it. Guth confirmed this in his later work. He famously said, "It is hard to build models of inflation that do not lead to a multiverse. The multiverse that arises from this process of eternal inflation is vast beyond any possible comprehension. It is not just billions of pocket universes, it is an infinite number. Every possible way that inflation could end happens an infinite number of times in different places. Every possible set of physical constants that could emerge from the decay of the inflaton field will appear somewhere. This leads to some extraordinary conclusions. In an infinite multiverse, everything that can happen does happen, not just once, but an infinite number of times. There are an infinite number of copies of the Earth, an infinite number of copies of you, infinite versions of you where you made different choices, and infinite universes with completely different laws of physics. Most physicists find this idea to be deeply unsettling. Science is supposed to be able to make predictions. But if anything that is possible occurs somewhere in the multiverse, then how can you predict what we should observe in our own universe? This is what is known as the measure problem. You cannot calculate probabilities in the usual way when you are dealing with infinity. Some physicists have embraced the multiverse as a feature of the theory, not a bug. It can explain the cosmological constant problem. In our universe, the energy density of the vacuum is incredibly small, about 10 to the power of minus 120 in natural units. Our theories suggest that it should be 10 to the power of 120 times larger. Such a massive discrepancy seems impossible to explain. But in a multiverse with an infinite variety, some of the universes will randomly have a small value for the vacuum energy. We just happen to live in one of those because any universes with a large value for the vacuum energy would not be able to form stable galaxies and stars. Observer selection does the rest of the work. Other physicists hate this kind of reasoning. They argue that it is giving up on fundamental physics. Instead of deriving the cosmological constant from first principles, the multiverse just says that it is an environmental accident, like asking why the Earth's distance from its star is 93 million miles. The answer is not some deep law of physics. It is just that we need the right distance to be able to support life. The debate over eternal inflation and the multiverse that it implies remains unresolved. Some researchers are looking for ways to be able to test the predictions of the multiverse. If other pocket universes collided with our own during the process of inflation, they might have left some imprints in the cosmic microwave background. These collision signatures would appear as specific patterns of temperature variation. So far, no such collisions have been detected, but the search continues. Advanced telescopes and detectors that are coming online in the next decade might be able to find some subtle anomalies that the standard single universe theories cannot explain. What is clear is that the theory of inflation, which was originally designed to solve some simple problems, has opened a kind of Pandora's box. It has transformed cosmology from the study of the universe into the contemplation of a multiverse. The Big Bang is no longer a unique event. It is just one event among an infinite number of others occurring eternally in an ever-expanding sea of space. We thought that discovering the universe was enough. Instead, we have learned that the universe is just the beginning. Alan Guth did not set out to destroy the uniqueness of our universe. He was a theoretical physicist who was struggling with a specific technical problem in the field of particle physics. The solution that he found in December of 1979 solved that problem beautifully. It also inadvertently implied that our universe is just one single bubble in an infinite and unending foam. Guth was thinking about magnetic monopoles. These are hypothetical particles that are predicted by the grand unified theories which attempt to merge 3 of the 4 fundamental forces of nature. The problem was that these theories predicted that these monopoles should be everywhere. Every single cubic meter of space should contain billions of them. Yet astronomers had never detected a single magnetic monopole. This was known as the monopole problem. Guth realized that if the very early universe had inflated exponentially, it would have diluted the monopoles to undetectable levels. Inflation would have spread the few monopoles that were created in the Big Bang across such vast distances that we would never be able to encounter one. Problem solved. He wrote "spectacular realization" in his notebook that night. But he also noted a serious issue with his theory that would take years to resolve. The original model of inflation assumed that the universe had started in a state that is known as a false vacuum, which is a temporary high-energy configuration that wanted to decay into a lower-energy true vacuum. As the false vacuum decayed, it would release energy, which would then drive the process of inflation. This decay happened through a process known as quantum tunneling, where bubbles of the true vacuum would form and then expand. The problem was that these bubbles would expand at the speed of light, but they could not catch up to the inflating space that was around them. The false vacuum that was between the bubbles would keep on inflating much faster than the bubbles themselves could grow. The bubbles would never be able to merge together to fill all of space. The universe would remain forever fragmented with patches of the true vacuum that were surrounded by the false vacuum. This did not match our observations. Our universe looks smooth and connected. Andre Linde and Andreas Albrecht, along with Paul Steinhardt, independently fixed this problem by modifying how the process of inflation ended. Instead of bubbles that were tunneling, the inflaton field would slowly roll down an energy hill, which would cause the process of inflation to end much more gracefully. This new inflation solved the fragmentation issue, but it also guaranteed that the process of inflation would be eternal, because the quantum fluctuations would always be pushing the field back up the hill in some regions. Guth and Linde both realized what this meant. If inflation was truly eternal, then it would produce an infinite number of separate pocket universes, each one with potentially different properties. The multiverse was an unavoidable consequence of the theory. Guth initially hoped that this conclusion was wrong. Perhaps some subtle effect would eventually shut off the process of eternal inflation everywhere. But a deeper analysis showed the opposite. Eternal inflation is actually more generic and harder to avoid than anyone had expected. By the 2000s, the idea of the multiverse had become respectable. Major cosmology conferences began to dedicate entire sessions to it. String theory, which is another attempt to unify the laws of physics, also predicted a vast landscape of possible vacuum states, which served to reinforce the concept of the multiverse. Guth and Linde became the spokesman for the idea that our observable universe is just one random sample from an infinite ensemble. This created both philosophical and scientific challenges. If we are living in just one single bubble among an infinite number of bubbles, then how can we possibly test our theories? Traditional science works by comparing predictions to observations, but multiverse theories often predict that every possible outcome will occur somewhere. How can you falsify a theory that is able to predict everything? Some physicists have argued that we should use what is known as anthropic reasoning. We observe what we observe because we exist. Any universes with very different properties would not be able to produce observers like us. So even in an infinite multiverse, we should still expect to find ourselves in a universe that is compatible with our own existence. This anthropic principle allows us to make probabilistic predictions based on which properties of a universe are the most conducive to life. Others find this kind of anthropic reasoning to be deeply unsatisfying. It feels a bit like giving up on finding deep explanations. Instead of asking why the physical constants have the values that they do, anthropic reasoning just says that those values are environmental accidents. In another bubble, they are different. We just happen to be in a life-friendly bubble. End of story. Guth himself is pragmatic about the idea of the multiverse. He acknowledges that it is a radical conclusion and one that makes the process of science much more difficult. But he also points out that science must follow where the evidence leads, even if it is to uncomfortable places. The theory of inflation is strongly supported by the observations of the cosmic microwave background. If inflation naturally leads to eternal inflation, and eternal inflation naturally leads to a multiverse, then we must take the idea of the multiverse seriously. The multiverse implies that our own cosmic history is a bizarre one. The Big Bang was not the beginning of all of reality. It was just the beginning of our own local pocket of it. Before our own bang, the larger inflating space already existed, and it was continuously producing new pockets. Some of those pockets formed earlier than ours. Some of them will form later. Our universe's age of 13.8 billion years is just the amount of time that has passed since the inflation in our own pocket ended. There might be no ultimate beginning at all. The inflating space could be eternally old with no first moment. Or there could have been some initial event that started the process of inflation. But that event is now lost in the infinite past, and it is inaccessible to us by any means. We are trapped in our own bubble, and we are unable to see beyond the horizon that light has had the time to cross. Guth's spectacular realization was actually more spectacular than he had ever imagined. He thought that he was just solving a problem about magnetic monopoles. He had accidentally discovered that we are living in an infinite cosmos where every single possibility is realized. The universe is not a single story. It is an infinite library where every single story has been written. Empty space is not as empty as it might seem. Quantum field theory, which is the mathematical framework that describes particle physics, reveals that what we call a vacuum is actually teeming with activity. Virtual particles are constantly popping in and out of existence. Fields permeate every single point in space. Energy fluctuates wildly at the very smallest of scales. These quantum properties mean that the vacuum can exist in different states, much like how water can exist as ice, liquid, or vapor. Each of these states has a different energy density. The lowest energy state is what is known as the true vacuum. Any higher energy states are known as false vacuums. If the universe is currently in a state of false vacuum, it could potentially decay into a lower energy state with some dramatic consequences. The idea of false vacuum decay was first analyzed in the 1970s by Sidney Coleman and others. They calculated how a region of false vacuum could be able to quantum mechanically tunnel into a state of true vacuum. The process begins with a random quantum fluctuation, which creates a tiny bubble of the true vacuum. This bubble has a lower energy than the surrounding false vacuum. This energy difference creates a pressure which causes the bubble to begin to expand. Once it has formed, the wall of the bubble moves outward at nearly the speed of light. Inside the bubble, the very laws of physics might be completely different from what they are on the outside. Particles could have different masses. Forces could have different strengths. The cosmological constant could change its value. For anyone who was inside the path of the bubble wall, the passage would be catastrophic. All complex structures would be completely disintegrated. The idea of false vacuum decay provides the mechanism for eternal inflation in many of the models. Imagine that the inflaton field starts out in a false vacuum with an enormous energy density. This high energy is what drives the process of exponential inflation. Occasionally, quantum tunneling will produce bubbles where the field has decayed to a lower energy state. Inside these bubbles, the process of inflation will slow down or stop, and a hot Big Bang will begin. But here is the twist that makes the process of inflation eternal. The false vacuum is still inflating in the space that is between the bubbles. Space is expanding so fast that even though new bubbles keep on forming, they can never fill all of the available space. The volume of the inflating false vacuum is growing much faster than the volume that is being converted to the true vacuum. Inflation is therefore able to continue forever in most of space, while pocket universes are forming as islands in this inflating sea. This picture has some profound implications. Our own universe is just such a pocket. The process of inflation ended here about 13.8 billion years ago, when our local patch of the false vacuum decayed. But beyond our own cosmic horizon, far beyond what our best telescopes could ever possibly see, the process of inflation is still continuing. New pockets are being formed constantly. Each of these pockets is causally disconnected from all of the others. The light from another pocket can never reach us because the inflating space that is between us is expanding too rapidly. The energy that is released during the process of false vacuum decay is what becomes the matter and radiation in the new pocket. This is a process that is known as reheating. The potential energy of the inflaton field is converted into a hot soup of particles. This is the Big Bang, the moment of maximum temperature and density. From that point on, the standard Big Bang cosmology takes over. The universe expands and cools. Atoms form. Stars ignite. Galaxies assemble. Different pockets might have different properties depending on how and where the false vacuum decayed. String theory suggests that the inflaton field can settle into many possible low-energy configurations, each of which corresponds to a different kind of particle physics. One pocket might have 3 generations of quarks and leptons like our own. Another might have 7. One might have a strong nuclear force that is twice as strong as ours. Another might lack the force of electromagnetism entirely. This diversity is what makes the multiverse a kind of laboratory that contains every possible experiment. Somewhere, a pocket exists where electrons are heavier than protons. Somewhere, atoms are not able to form. Somewhere, chemistry is completely unrecognizable. And somewhere tucked into a corner with just the right properties, observers are able to evolve and wonder why their own universe seems to be so finely tuned for life. But could we still be in a false vacuum? Could our current universe be in a metastable state capable of decaying to an even lower energy state? Calculations have suggested that this is a possibility. The measured mass of the Higgs boson and the top quark place our universe very near to the boundary between stability and metastability. Small changes in either of these values would push us definitively into the false vacuum regime. If we are in a false vacuum, then a decay could happen at any moment. A bubble of the true vacuum could nucleate anywhere in space tomorrow. Once it had formed, it would expand at the speed of light. We would have no warning at all. The bubble wall would arrive without any announcement, and it would erase everything that we know. The interior of the bubble might be able to support a different kind of physics, but it would probably not be able to support chemistry or life as we understand it. Fortunately, the calculations indicate that such a decay is extraordinarily unlikely to happen on human timescales. The probability per cubic meter per year is absurdly small, many orders of magnitude below anything that we could possibly detect. The universe could persist in its current state for durations that would vastly exceed its current age. By the time a false vacuum decay becomes a likely event, all of the stars will have already died and all of the black holes will have evaporated anyway. Still, the idea that reality itself could collapse at any instant remains a disturbing one. It also offers a strange kind of immortality to the multiverse. Even if our own pocket universe eventually decays countless, others will continue to exist unaffected. The multiverse as a whole is eternal. The individual pockets are only temporary. The false vacuum is both a trap and a gateway. It traps us in a temporary island of stability, but it also serves as the gateway through which new universes are born. We are all living on borrowed energy. Look around you. Space has 3 dimensions. You can move forward and backward, left and right, and up and down. If you add time as the 4th dimension, then you have the space-time of relativity. 4 dimensions are able to explain everything that we observe. Or do they? String theory, which is the leading candidate for a theory that can unify quantum mechanics and gravity, requires more dimensions. Not just 1 or 2 extra dimensions, but 6 additional spatial dimensions beyond the 3 that we are able to see. That means that space has 9 dimensions, and if you add time, that makes 10. In some versions of the theory, which are known as M theory, there are 11 dimensions in total, This seems absurd. Where are all of these extra dimensions hiding? The answer is that they are curled up so small that we are not able to detect them. Imagine a garden hose that is being viewed from very far away. It looks like a one-dimensional line. It is only when you get up close that you can see that it has a thickness with a circular dimension that is wrapped around its length. The extra dimensions of string theory are similar, rolled up into microscopic shapes that are smaller than subatomic particles. These hidden dimensions are not just mathematical artifacts, they have a profound effect on the laws of physics. The size and shape of these extra dimensions are what determine the properties of the particles and forces in the visible dimensions. A string that is vibrating in 10 dimensions can produce different patterns depending on how those extra dimensions are configured. Each one of these patterns corresponds to a different kind of particle. This gives string theory a tremendous amount of flexibility. By choosing different geometries for the extra dimensions, you can reproduce the particles and forces of the standard model. You can also produce entirely different kinds of physics. String theorists have estimated that there are roughly 10 to the power of 500 possible configurations of these extra dimensions. Each of these configurations will give a different kind of low-energy physics. This vast landscape of possibilities is both a blessing and a curse. It explains why string theory is able to accommodate so many of the features of nature. But it also means that the theory does not uniquely predict the properties of our own universe. Many different compactifications could produce a kind of physics that is similar to what we observe. Without a principle for being able to select the right compactification, string theory loses its predictive power. The extra dimensions have another remarkable property. They allow for the existence of extended objects that are larger than one-dimensional strings. A two-dimensional surface that is extending through space is what is known as a membrane or a brane. Higher dimensional objects are also possible. A familiar three-dimensional space might actually be a three-brane, a kind of sheet that is embedded in the higher dimensional space. This brane world picture revolutionized the field of cosmology in the late 1990s. Physicists realized that if we are living on a brane, then the particles and forces that we know about might be confined to that brane. Only gravity would be able to propagate through the full higher dimensional space, which is known as the bulk. This could explain why gravity is so much weaker than the other forces. Gravity is diluted across the extra dimensions, while the electromagnetic and nuclear forces stay concentrated on our own brane. The brane world concept led to the development of the ekpyrotic scenario, which was proposed by Paul Steinhardt, Neil Turok, and their collaborators in 2001. This model suggests that our universe is a three-brane that is floating in a higher dimensional bulk. Nearby, separated by a gap across an extra dimension, there is another parallel brane that is floating. These two branes are attracted to each other by the gravitational forces that are acting through the bulk. Occasionally, these branes will collide. When they crash together, the collision releases an enormous amount of energy. This energy then appears as hot matter and radiation on the surfaces of the branes. From the perspective of anyone who is on one of these branes, this event would look like a Big Bang, but it is not the beginning of space or time. It is just a collision event in an ongoing history. After the collision, the branes would bounce apart, move back through the bulk, slow down, and then eventually start to approach each other again. The cycle would then repeat. Each collision would be a new Big Bang. Each separation would create time for a universe to be able to evolve before the next collision. This is the cyclic ekpyrotic model. The extra dimension plays a crucial role in this process. The distance between the branes changes as they move through this dimension. When they are far apart, the distance grows as the universe expands. When they collide, the extra dimension momentarily shrinks down to zero before it begins to grow again. This provides a natural mechanism for generating the cycles without ever having a singularity where all of the dimensions collapse. The ekpyrotic scenario makes some specific predictions about the cosmic microwave background that are different from those of standard inflation. It predicts that there will be less production of gravitational waves and that there will be different patterns in the temperature fluctuations. Our observations so far seem to favor inflation, but the differences are very subtle. More precise measurements might be able to distinguish between the two models. String theory's extra dimensions also have an effect on black holes. A black hole in 4-dimensional spacetime has a very simple geometry, but a black hole in 10 dimensions can have very complex topologies that involve the extra dimensions. These higher dimensional black holes might behave differently, which would affect how they form, how they merge, and how they evaporate. Some string theorists have speculated that the Big Bang itself was a higher dimensional black hole. From the outside, it would look like a collapsing object. From the inside, it would appear as an expanding universe. This black hole cosmology remains highly speculative, but it shows how the extra dimensions can provide new ways to think about the origins of the cosmos. Critics point out that the extra dimensions of string theory have never been observed. No experiment has ever detected even the slightest hint of any dimensions beyond the familiar 3. The mathematical elegance of the theory does not guarantee its physical reality. Many physicists suspect that the true theory of quantum gravity might not require any extra dimensions at all. Nonetheless, the idea that space has a hidden structure has had a profound influence on modern cosmology. It has opened up conceptual possibilities that researchers are continuing to explore. The ekpyrotic model, the idea of brane collisions, and the concept of cyclic universes all flow from taking the idea of extra dimensions seriously. Reality might have more directions than we can possibly imagine, and what we call the universe might just be a surface in a much deeper and more complex space. Picture 2 enormous sheets of reality floating through a higher dimensional void. Each of these sheets is a 3-brane, a 3-dimensional surface that is extending infinitely in the directions that we experience as space. These branes are separated by a small gap in an extra dimension that we cannot see. They are being pulled together by a gravitational attraction that is acting through the bulk. As the branes approach each other, they begin to accelerate. The gap between them narrows. At some point, they collide with a tremendous amount of energy. The collision heats both of the branes to extraordinary temperatures. Matter and radiation flood across their surfaces. From the perspective of any observer who is on one of these branes, this event would appear as a Big Bang, a sudden transition from a state of cold emptiness to a hot, dense state. This is the central mechanism of the ekpyrotic scenario. The word ekpyrotic comes from an ancient Greek philosophy which referred to a cosmology where the universe is born from fire and then returns to fire in an eternal cycle. The modern ekpyrotic theory translates this idea into the mathematics of string theory. The fire is now understood as being the enormous energy that is released when two branes collide. The rebirth is the new universe that forms on those branes after the collision. The cycle is able to continue indefinitely. The ekpyrotic model is able to address several deep cosmological puzzles at the same time. Let's start with the flatness problem. Our universe has a spatial geometry that is very nearly flat, but in the standard Big Bang theory, flatness is an unstable state. Any slight deviation from a state of perfect flatness would be amplified over time. For the universe to be as flat as we observe it to be today, it must have been extraordinarily flat at the very beginning. Why? In the ekpyrotic cosmology, flatness emerges naturally. During the slow approach that occurs before the brane collision, the universe on each of the branes is slowly contracting. This contraction automatically smooths out any spatial curvature. Imagine a wrinkled sheet that is being gently compressed. The wrinkles will naturally flatten out. By the time the collision occurs, the geometry is nearly perfectly flat. No fine-tuning is required. The horizon problem also finds a solution in this model. Different regions of the cosmic microwave background have nearly identical temperatures, despite being too far apart to have ever been in communication with each other at the speed of light. How did they manage to coordinate themselves? Standard cosmology invokes the process of inflation to make these distant regions start out close together. But the ekpyrotic cosmology uses the contracting phase. During the contraction, the regions that are now separated were once in causal contact with each other. They were able to equilibrate back then. The scenario also makes some specific predictions about the primordial density perturbations. These are the tiny variations in the density of matter that eventually grew into the galaxies. In the theory of inflation, quantum fluctuations during the period of exponential expansion are what produce these perturbations with a nearly scale-invariant spectrum. Different-sized regions have similar amplitude fluctuations. The ekpyrotic cosmology is able to produce a similar spectrum, but it does so through a different mechanism. The quantum fluctuations that occur during the contracting phase get amplified as the branes approach their collision. The amplification is scale-dependent in just the right way to be able to match the observations. Crucially, the ekpyrotic models predict that there will be almost no gravitational waves, unlike the theory of inflation, which produces a significant gravitational wave background. This difference provides a clear observational test. Experiments like LIGO and any future space-based detectors are aiming to measure these primordial gravitational waves. If they find waves at the level that is predicted by inflation, then the ekpyrotic cosmology will be ruled out. If they find much weaker signals or none at all, then the ekpyrotic models will gain a significant amount of credibility. The current observations slightly favor inflation, but the sensitivity is not yet high enough for a definitive verdict. The cyclic version of the ekpyrotic cosmology extends the single collision into an infinite series. After each collision and expansion, the branes will eventually fall back together for another collision. Dark energy plays a crucial role in this process. The accelerated expansion that we are observing today, which is being driven by dark energy, is interpreted as a force that is pushing the branes apart. But this force is not repulsive forever. At large separations, the attractive force will come to dominate, and it will begin to pull the branes back together. This sets up a kind of cosmic rhythm: collision, expansion, a turnaround, a contraction, and then another collision. Each complete cycle might last for several trillion years. Our current universe, at 13.8 billion years old, is just in the early part of one of these cycles. Eventually, in the unimaginably distant future, the expansion will halt and a contraction will begin. The universe will shrink slowly over trillions of years until the next collision ignites a new Big Bang. One of the fascinating implications of this idea is that the future and the past are connected. The far future of our own universe will become the pre-collision state for the next cycle. This means that studying the eventual fate of our cosmos might be able to reveal some clues about what came before our own Big Bang. The physics of dying universes and newborn universes are linked together. Some physicists find the cyclic ekpyrotic model to be more satisfying than the theory of eternal inflation because it avoids the idea of the multiverse. There is only one single universe which is going through a series of cycles, not an infinite number of bubble universes with different laws of physics. This makes the theory much more predictive. We are not asking the question of why our own universe has certain properties out of an infinite number of possibilities. We are asking how the cyclic dynamics are able to select those particular properties. Critics point to several unresolved issues with the model. The singularity at the point of the collision remains a problematic aspect. String theory should be able to resolve it, but the calculations are currently beyond our techniques. There are also some questions about entropy. Does the entropy get reset at each collision, or does it accumulate? If it accumulates, then each cycle should become longer and more chaotic. Our observations do not show any signs of such a progression. Despite these challenges, the ekpyrotic scenario represents a form of bold thinking. It takes seriously the possibility that time is truly infinite in both directions. The universe has no beginning and no end. It cycles through a series of phases like the seasons, with each one setting up the next. We are currently living in the spring of one cosmic year, with an autumn and a winter eventually ahead of us, which will then be followed by another spring. The ancient Stoics had no mathematics, no telescopes, and no quantum mechanics. Yet their intuition about the eternal cycles of the universe captures something that modern physics is increasingly considering to be plausible. Perhaps humans have always had a sense that reality is older and stranger than any single beginning can possibly explain. There is a number in the field of physics that is so puzzling that Steven Weinberg once called it the bone in our throat. This number describes the energy of empty space itself. Quantum field theory predicts that its value should be enormous, about 120 orders of magnitude larger than what is actually observed. This discrepancy is so vast that it almost defies comprehension. It is the worst theoretical prediction in the entire history of science. The number is known as the cosmological constant, and it is denoted by the Greek letter lambda. Einstein first introduced it in 1917 as a modification to his theory of general relativity, but he later abandoned it, calling it his biggest blunder. But astronomical observations in 1998 revealed that lambda is not actually zero. Empty space does have an energy. It is what is causing the expansion of the universe to accelerate. We can see this acceleration when we measure distant supernovae. They appear to be dimmer than we would expect, which indicates that they are at greater distances than a standard expansion would produce. The problem is that quantum mechanics predicts that the vacuum should be seething with energy. Virtual particles are constantly popping in and out of existence. Each type of particle contributes to the energy of the vacuum. If you add up all of the contributions from all of the different particle types up to the Planck energy scale, you get a vacuum energy density of about 10 to the power of 93 grams per cubic centimeter. This is a fantastically large number, but our actual measurements show that the vacuum energy density is only about 10 to the power of minus 27 grams per cubic centimeter. The ratio between the theory and the observation is about 10 to the power of 120. To visualize this, if the theory had predicted that someone's height was 1 meter, then their actual height would be smaller than the size of an atom compared to the size of the observable universe. No other physical quantity has such a ridiculous mismatch between theory and observation. So why does this matter? Because if the vacuum energy were even 1,000 times larger than what is observed, then galaxies would not be able to form. The accelerated expansion would tear apart any structure before the stars could even ignite. A universe with a large value for the vacuum energy would be empty and sterile. The fact that lambda is tiny but not zero is what allows complex structures like galaxies, stars, planets, and even us to be able to exist. Some physicists had hoped that lambda was exactly zero due to some unknown symmetry, which would at least have been an elegant solution. But the observations that show that lambda is small but positive have ruled out this explanation. The universe does have a vacuum energy. It is just incredibly less than what our theories predict. So why is this cyclic cosmology offers a potential answer to this question? If the universe is going through an infinite number of cycles, then the cosmological constant could be decreasing over time. Each cycle would bleed off some of the vacuum energy. After countless cycles stretching back into the infinite past, lambda would have relaxed to a very tiny value. We are observing this small value for the constant not because our own universe is special, but because it has aged through many, many cycles. This explanation appeals to the physicists who dislike the idea of anthropic reasoning. The alternative explanation, which is favored by the advocates of the multiverse, is an environmental one. In the theory of eternal inflation, different pocket universes have different values for lambda, which are selected randomly from a vast landscape of possibilities. Most of these pockets have a large value for lambda, and so they remain empty. We just happen to be living in a rare pocket with a small value for lambda because only such pockets are able to produce observers. We observe what we must observe in order to exist. The cyclic models are able to avoid this kind of anthropic logic. There is only one single universe with one single value for lambda, and that value is the result of the cosmological evolution that has occurred through the cycles. The theory makes a definite prediction that lambda should be small today, and it provides a mechanism for why this is the case. This is more satisfying to the physicists who want to find fundamental explanations rather than just selection effects. However, the cyclic explanation does face some challenges. If lambda is decreasing with each cycle, then it must have been larger in the past cycles. But if it was too large, even just a few cycles ago, then the universe would have accelerated too fast for any structures to have been able to form. How did the cyclic process get started? There seems to be a fine-tuning problem that is just being pushed back to the earlier cycles. Another approach uses the landscape of vacuum states that is predicted by string theory. Perhaps there are thousands of competing effects that all work to determine the value of lambda, with each one of them pulling it in a different direction. The observed tiny value would then be the result of a delicate cancellation among all of these different effects. But this seems a bit contrived. Why would nature arrange for such a perfect cancellation? Some physicists have argued that we simply do not understand quantum field theory well enough. The calculation that predicts a huge value for the vacuum energy might just be wrong. Perhaps there are some fundamental principles that we have not yet discovered that would naturally make lambda small. Supersymmetry, if it exists, could provide a partial cancellation. But even supersymmetry would only reduce the discrepancy from 10 to the power of 120 to 10 to the power of 60. This is still an absurdly large number. The cosmological constant problem is deeply connected to the theory of quantum gravity. At the Planck scale, where the effects of quantum mechanics and the effects of gravity become equally important, space itself becomes quantized. Our current calculations are all assuming that spacetime is a smooth continuum. Maybe that assumption fails at the Planck scale, and a corrected calculation would give a small value for lambda. Loop quantum gravity and other approaches to quantum gravity might be able to resolve the problem, but no complete calculation exists yet. We are still stuck with the mystery. The energy of the vacuum is tiny, yet the universe is accelerating. This small constant is what dominates the evolution of the cosmos, and it will be what determines the ultimate fate of everything. In the far future, tens of billions of years from now, dark energy will overwhelm the force of gravity everywhere. The galaxies will separate from each other beyond each other's horizons. The stars will exhaust all of their fuel. The black holes will evaporate. Eventually, only isolated particles will remain in an exponentially expanding void. This is what is known as the heat death scenario, a cold, empty future with no possibility of any new structure ever forming. But if dark energy is cyclic, then this heat death can be avoided. Before the universe becomes completely cold and empty, the cycle will reverse. A contraction will begin. The universe will heat up again. New structures will be able to form in the next cycle. The cosmos is able to avoid an eternal stagnation by periodically refreshing itself. This raises some questions about entropy. The second law of thermodynamics states that entropy is always increasing. Each cycle should therefore be more disordered than the last. How can the universe keep on cycling indefinitely if the disorder is constantly accumulating? Some of the cyclic models have proposed that the universe grows slightly larger with each cycle. This extra volume would provide more phase space for the entropy to be able to spread out into. The entropy would increase in absolute terms, but it would decrease relative to the available volume. This would allow the cycles to be able to continue without violating the laws of thermodynamics. Others have suggested that black holes are what reset the entropy during the transition. Black holes have an enormous amount of entropy. When they evaporate at the end of a cycle, they release that entropy in the form of radiation. That radiation would then be recycled into the next cycle, in a way that would produce low entropy initial conditions. The details of this process remain speculative. What is clear is that dark energy is central to our understanding of the history of the cosmos. It is not just affecting our current era, it is connecting the past, the present, and the future. The force that is accelerating the galaxies today might be the descendant of whatever it was that ended the previous universe, and the ancestor of whatever it is that will end our own. Dark energy is not the mysterious afterthought that it appears to be in our standard cosmology. It might just be the conductor that is orchestrating the universe's eternal symphony.